Alright, today we are going to do exponential growth and decay. Mathematical models in which the rate of change of a variable is proportional to the variable itself are common in both business and scientific worlds. Many of you might have seen this in physics. Suppose that the rate of change, which is dy over dt, is proportional to y itself. So k is a constant, guys. So k is a number, and then y is the amount of substance presented at time t. So what we're going to do is actually solve for this equation. We have dy over dt equals ky. So with what we learned last time with differential equations, we need to move our y's with our dy's and move this dt and move it on the other side. So we get 1 over y dy equals k dt. We're going to take the integral of both sides. That gives us ln, absolute value of y, equals, and this is the constant, so we'll get t, kt, plus c. Don't forget we have to have that plus c. We only have to do to one side, not both. Excuse me. Alright. Now let's get rid of the ln. So if we get rid of the ln, we're going to e both sides, and I get the absolute value of y equals e to the kt plus c. I'm going to do two things here at once, so if you have to stop this and rewind it again, it's okay. So usually when you have an absolute value, you think of this as plus or minus, correct? But the idea is with the plus or minus, either way that c, it cancels. So we don't need to have that plus or minus there because c can be any constant. And when we add exponents, it means that we actually multiplied the two terms. Okay. Again, there would have been a plus or minus up front, but plus or minus is all depending on that c. C is a constant. E to a constant is just another constant. So I can make this whole term right here the value of c, because it is some constant. So y equals c e k t. This is the basic law of exponential growth or decay. C is a constant, k is our proportional constant, y and t are your variables based on time, and our result. So there are some facts down here you want to go over. C is the initial value, so that's what we start with. K is the constant of proportionality. So that's your rate, guys. That's what you grow or decay by. T is your time, and Y is your amount present at that certain time. So let's do one example here. What is the rate of growth? So we are finding K. What is the rate of growth of population in a city whose population triples every 100 years? Assume that the population growth can be modeled by the basic law. Okay, so let's start with the basic law. We get y equals c e k t. What we don't know is the initial amount. But we know with whatever we start with, 100 years after, we're 3 times. So I'm going to put that in view. So if we start with a C amount, in 100 years, so I'm going to make t 100, our value is 3c. Okay, so again, in 100 years, our original amount triples, so I can use that. As you can see, what happens, since this is all multiplication, to get rid of c, we would divide, leaving 3 equals e, and I'm going to put the 100 in front of the k. So the c's actually cancel. Now, I need to get k by itself. So I need to get rid of the e, so I'm going to ln both sides. I get ln 3 equals 100k, and then to get k by itself, I just divide by 100. In your calculator, because it wants you to express it as a percent, I'm going to do that now. ln 3 divided by 100. If we talk about a percent, we need to move over it twice. So our final is 1.1% is how it's growing. Very good. Let's try some other questions that involve the exponential growth and decay. Let y represent the mass in pounds of a radioactive element whose half-life. So we're dealing with the same situation, except it's half the original amount in 4,000 years. If there are 200 pounds of the element in an inactive mine, so that's actually our C. How much will remain in 1,000 years? So we are saying, what is y when t equals 1,000? Well, what are we missing? What did it not say anything about? It didn't say anything about k. So that means we have to solve for k first. We can solve by k with using this amount of a half-life in 4,000 years. So I can either use the value of c or just use the actual variable of c because they cancel. So half of 200 is 100. We started with 200, e to the k, and of course half of it happened in 4,000 years. So now let's solve. First we divide by 200 and we get that 1/2. Do you guys see, if just like on example 1, we have used 1/2 c, the c's cancel and we still have the 1/2. Okay. Alright, so now let's solve for k here. We're going to ln both sides. So we get ln 1/2 equals 4,000 k. And then we know that k equals ln 1/2 of 4,000 over 4,000. Now, this number is a decimal, and we're going to use that to answer our following question. Okay. Now, we're going to learn a trick on our calculator right now, because what happens is when we plug this in, so I'm going to show you, hold on, let's back up here. I'm going to answer the original question. So we're going to say how many or how much of the original 200 is still there after 1,000 years. Now we are going at the rate of ln 1/2 over 4,000. We are going for 1,000 years. Okay, as you can see, this gets a little hefty on our calculator with parentheses. If you want, you can still write this in, but here's another way to do it. Originally we solved for k, right? And that was ln 1/2 divided by 4,000. I also want to make sure I don't estimate around this because it messes up our whole problem. So what I'm going to do is go to the bottom of my calculator and I'm going to go to the STO button. Push that. What I'm doing is I'm storing it. So what I need to do is now give it a letter. Don't use X or Y because that gets confusing. So I'm going to go to alpha and maybe put A down. So I'm going to store it as A. Press enter. So I just stored that value as A. The reason why this helps is because when I plug this in, I'm going to put A right here. So I go 200 E, and then I'm going to have 1,000 times A. So instead of dealing with all those parentheses, I'm going to put the value of A in there and enter. And there is my answer. So we are left with 168.179. Don't forget your units. This is talking about pounds. Okay, so a couple of tricks here with that store button. Alright, last example. Newton's law of cooling states that the rate of a change in temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. Suppose a metal figurine heated at 150 is brought to a room temperature. So here we go, 72 is our room temperature. It will not get cooler than 72. That is the temperature of the surroundings, okay guys? If the figurine cools from 150 to 120 in 15 minutes, how long will it take for the figurine to reach 100? Okay, so this is our final question. We are looking for T when Y is 100. We also know that when Y is 120, T is 5. Yet again, what's the one thing we're missing? Yes, we are missing the initial, right? And we are missing, or that initial change I should say, because it's the difference between the temp. And we are missing K. So let's see what we can put at first. I know that at 150 we're going to 72 degrees. We're trying to figure out that initial change. And that is going to be our initial time, right? Because we're starting at 150. So that's at time 0. As we are able to solve this, I get 78 equals C times, well, e to the 0 is 1. So C is 78. Alright, now we're going to use our next thing we know. We know when T is 5, Y is 120. So, At 120, going down to our room temp, we start with the change of 78 degrees, and we know that in 5 minutes, that's where it's going to be taking us. So let's solve for K. We get 48 equals 78 e to the 5k. So let's start solving. We get 48 over 78 equals e to the 5k. Our next step would be ln both sides. And then divide by 5. So k equals, so our rate of change is ln 48 over 78 all over 5. Now we can use that to figure out how long it takes for 100 degrees to get down to 72. 100 minus 72 equals 78e. Now our k is this huge number. So of course, as you're writing this down, what would be easier to do in solving? Probably storing that in, right? So I'm going to store that in. Let's see, ln 48 divided by 78 divided by 5, and then I'm going to store it, so STO, I'll store this one as B. Now I'm going to put B right on top of there so I know what I'm going to make it in the calculator. Because we are solving for, I put K but it's supposed to be T, sorry guys. Because I'm solving for the time, I have to do some algebra before I can plug it in my calculator. So 100 minus 72 equals 28. So I get 28 equals 78 e. I'm going to say b to the t so it's easier to write. I get 28 divided by 78 equals e to the b t. ln both sides, so ln 28 over 78 equals bt. So now in my calculator, I'm going to do that division because all I have to do is divide by b. So let's check that out in the calculator right now. I'm going ln 28 divided by 78, and then I'm going to divide by that b. Luckily I stored it so I don't have to worry about parentheses. And I got the wrong answer. Why? So guys, I realized I got the wrong answer, and that's because it should be 15, not 5. So hopefully many of you caught that before you kept going. But if not, now you know, go back, and it's 15. So I need to reset this in my calculator. So ln 48 divided by 78 divided by 15, enter, store. I'm going to put it in as B. There we go. Okay. Now let me do this. ln 28 divided by 78 divided by B. There we go. Correct answer. So it says express your answers to the nearest minute. So we're going to round this. This is closer to 32 minutes. Now guys, if you were doing this with me and didn't notice my mistake of 15, I'm going to keep it in the video because really we make all these mistakes all the time. So we have to make sure that we go back to what we're looking at. Okay? If you have any questions, come call me over.